Okay, we're going to finish up our statistics with chapter 8 when we talk about hypothesis testing. Now, hypothesis testing is where we move from descriptive statistics into the realm of inferential statistics. We did this a little bit before when we were looking at confidence intervals. Now we're going to actually formalize the process. Hypothesis testing is all about staking a claim on something, using some scientific evidence to support that claim or not support that claim, and then coming to a conclusion about that. What we're really doing here is using mathematics to support the scientific method, which you may have learned about in your science classes before. So the main objective of this chapter is to develop the ability to construct these hypothesis tests for claims made about proportion, P, and a population mean, mu. In other words, we're using small samples to make predictions about the population as a whole. And this is the main goal for this course. You can also do a hypothesis test for all kinds of other things as well. And we looked a little bit at correlation when we looked at chapter 3, when we made some conclusions from that. But you can also use it on a test for variance. For this course, we're going to focus on just the proportion and just the mean. Some examples of some things that you can use for a hypothesis test is you can claim that the XSORT method allows couples to increase the probability of having a baby girl. We'll actually explore this as an example of a hypothesis test. You can do in business here, pricegrabber.com survey of some subjects claim that a majority have heard of Kindle as an ebook reader. Part of what we're going to learn is how to codify what a majority is, and that's, the probability is greater than 50%. So when you see a majority, you want to be able to understand what that means. And also in health, it's often claimed that the mean body temperature is 98.6 degrees. We can test this claim using a sample of 106 body temperatures with a mean of 98.2. We'll look at that example in a future video. A little bit of caution though, is that we can use this hypothesis testing as long as the data that we're getting is legitimate. You're using a simple random sample. The source of your data is good. Your sampling method is good. You have to make sure that all of these things are actually valid before you actually conduct your hypothesis test. And so we're going to assume for the most part that these things are going to be valid. But you want to be careful when you're actually using a hypothesis test in the field. You want to make conclusions about your data that is relevant. So just a general overview is we want to be able to understand the following. We're going to look at how to identify something called the null hypothesis and the alternative hypothesis, and that's going to be some given claim that we're making about our data. We're going to use a sampling distribution that's relevant. Are we doing a proportion test? Then we're going to use the normal distribution. Is it going to be a mean test? Then we're going to use the t-distribution that we learned about in the last chapter. Then we're going to find the value of the test statistic from a given claim and sample data using StatCrunch. We're going to use StatCrunch to do all of our calculations for us again. We're going to identify the p-value, and then we're going to compare it to some sort of alpha. And this alpha we'll talk about later, but that's something that you get to pick as far as how well your test is going to be. Then we're going to state a conclusion about the claim in simple and non-technical terms. So a couple of vocabulary words. A hypothesis is the actual claim or statement about a property of a population. In other words, where half of the people like green eggs and ham. The average age of students going to UNE is 19.5. The hypothesis test is the procedure that we use for testing this claim about this property of a population. Now, all of this and what we're doing is based upon this rare event rule for inferential statistics, which means that if under a given assumption, the probability of a particular observed event is exceptionally small, we conclude that the assumption is probably correct, not correct, okay? In other words, if we say the probability that the moon is made of green cheese is 1%, it's probably not made out of green cheese, okay? This is our rare event rule of inferential statistics. Now, if we test that hypothesis and we send somebody to the moon and they land on the moon, they say, oh my goodness, it's made of green cheese, then we're actually going to prove that hypothesis of what we have, okay? So we have this concept called a null hypothesis. And this null hypothesis doesn't mean nothing's happened, just means we have H sub 0. It's a start point that we use to judge whether our hypothesis is going to be valid or not. And we're going to test that null hypothesis directly in the sense that we assume it to be true. And then we're going to reach a conclusion. We're either going to reject or we're going to fail to reject that null hypothesis. Those are the two things that conclusions that we're going to make about our null hypothesis. And we'll come back to reject or fail to reject. It sounds like we reject or accept the null hypothesis, but fail to reject, even though it's a double negative, is a better way of looking at it. The alternative hypothesis that we come up, which is denoted by H1 or HA, is some statement that the parameter has a value that differs from the null hypothesis. Is it less than, is it greater than, or is it not equal to that null hypothesis? And these are the three inequalities that we are going to use with the alternative. And these symbols are based upon that claim. That claim has, if the claim has this condition of equality, meaning that the claim has an equal sign in it, meaning that the claim is equal or less than or equal to or greater than or equal to, then the alternative is going to be the opposite of that claim. If the claim does not have that condition of equality where it's not equal to, strictly less than, or strictly greater than, then the alternative is going to be the same as the claim. We're going to use that same value. If we look at this sheet that we have here, if we make the claim that P is greater than 0.5 or less than 0.5 or not equal to 0.5, then the alternative is going to be the same as the claim. We're not going to make any changes here. However, if our claim is less than or equal to, greater than or equal to, or strictly equal to, we're going to flip all of these. In other words, less than or equal to is going to become greater than. Greater than or equal to is going to become less than. And equal to is going to become not equal to. Now, the ones that we actually use the most are greater than, less than, and equal to. So most of the time you won't be flipping it except if your claim is that it's equal to something. At the end, you're going to have your alternative hypothesis is going to be greater than, less than, or not equal to. In either one of these cases, these are the only choices that you're going to have. Now, if you're going to conduct your own test, here's a little note about forming your own hypotheses. You want to be able to support your claim, or instead of failing to reject your claim, which is not strong, you want to be able to support your claim. You want your claim worded in such a way that it becomes the alternative hypothesis, meaning that you want to use greater than or less than, okay? Those are the really strong ones to do. We can use equal to be not equal to, but it's a less strong of a claim. Here's an example. Let's say that we're going to assume 100 babies are born to 100 couples treated with the X sort method of gender selection. That comes from the X chromosome, Y chromosome for gender. And it's going to claim that girls are more likely. Great. So we're claiming that it's going to be greater than 50%. So our null hypothesis is P is equal to 0.5. Now your null hypothesis is always going to be an equal sign. It's always equals. And then our claim is that it's going to be greater than. So this way for you guys in the video. Okay. So your claim is going to be greater than. So your alternative is going to be the same as our claim. We actually conduct an actual experiment. We'll come back to this example. We observe 58 girls and 100 babies. So our proportion that we get is 58%. The next thing you're going to decide is some sort of significance level. This is your alpha that you have. When we had confidence intervals, your alpha was evenly distributed between your two tails. In a hypothesis test, it can be in your two tails still, just like in a confidence interval, or it may be all in the left tail, or it may be all in the right tail. And that depends upon your claim and your alternative hypothesis. Here's what a two-tailed test will look like. You have your null is equal to, and you have your alternative is not equal to. Your alternative hypothesis is what determines what type of tail test that you have. Here, our alpha is going to be evenly divided between the two tails in our critical region. In a left tail test, we're going to go to the left here. And in a right tail test, we're going to go to the right. All of your alpha is going to be in the right tail here. Okay? Just like up here, all of your alpha is going to be in the left tail. Now, your critical value is something that you can use given your alpha to find some sort of z-score that's going to separate your rejection region, which is your tail, from the rest of it. We're not going to be using critical values in this class. That's a traditional method of hypothesis testing. But because we're using StatCrunch and we can generate something called p-values, we're going to use the p-value method to make that happen. If you were interested in the math that goes behind it, the requirements for the proportion test is that your n times your p has to be greater than or equal to 5, meaning that n represents your sample size and then p actually represents the null hypothesis, the value of that null hypothesis. You have to multiply them together and have to be greater than or equal to 5. Same with n and q. And remember, p and q add up to 1. You're not going to have to worry about this too much, but just remember that your samples have to be of decent size, and then your claims can't be 0.01, 0.02 unless you have a decent size sample, okay? Your test statistic, you can calculate using this formula. Now, when we do the mean test, it's going to look the same as a confidence interval on our mean. We can use a normal distribution. If your population is normally distributed, then everything is fine. But if your sample size is greater than 30, then you can use that as well. And here's how you calculate your t-value for your test statistic. Looks a lot like the central limit theorem, and yes, they're very, very similar. So now this test statistic is a value used to making a decision about this null hypothesis. And it's found by converting the sample statistic to a score with the assumption that the null hypothesis is true. So now we're going to use StatCrunch to actually find this value of the test statistic, and then StatCrunch will also calculate the p-value that we get. So let's go back to our example where we had the XSort method of gender selection. And in our example, we had 58 girls for 100 couples. And we're claiming that this XSort method is going to be greater than 50%. So here, our claim is that p is greater than 0.5. So our null hypothesis, or H0, that's going to be p is equal to 0.5. Remember, the null is always equal. And since our claim is an inequality where it's greater than and does not have that condition of equality, our alternative is going to be the same as our claim here. So we're going to use strictly greater than. So now we can calculate what our p hat is. This is our sample proportion, and that's going to be 0.58 because that's 58 girls out of 100. This PowerPoint's already available to you in your document sharing. I'll also send it to you again. If you forget what these symbols are, you can come back to this slide. So now if you were calculating this by hand, this is what you would come up with. You would calculate your answer and you would get 1.60. This is a z-score. This represents the number of standard deviations from the mean where the sample proportion falls. Now remember, the empirical rule is still working here. Is that usual or, within the range of 2 standard deviations? And we can see that 1.6 is not really an unusual value. If it was greater than 1.96, which is 2 standard deviations from the mean, now we're talking the unusual territory. The hypothesis test picks these values on a little finer method that we had, different from what we had before when we were just talking about 2 standard deviations from the mean. We're picking some values that are going to be a little bit more finer grained. All right, so there's our calculation. But now we're going to use the p-value method, and I'll show you how to use StatCrunch in the next video that we have. But this p-value is going to be a decimal. It's going to be between 0 and 1. And you're going to compare that p-value to your alpha. Now, if your p-value that you get is less than or equal to your null hypothesis, if your p-value is less than or equal to your alpha that you have, you're going to reject the null. If your p-value is greater than your alpha, you're going to fail to reject the null. Now, in some cases, rejecting or fail to rejecting, they're both right, depending upon what type of test that you're doing. So go back to our example. We got a test statistic of 1.60. We calculate our p-value to be 0.0548. So we picked an alpha of 0.05, and 0.0548 is going to be greater than our alpha. So in this case here, we're going to fail to reject the null because our p-value here is going to be greater than our alpha. This is the important part. This is where we make the conclusion about our test. If the p is high, the null will fly. If the p is low, the null must go. Okay? So we fail to reject. That means it flies. That means we kind of accept it. So that is how that all works. Now we state the final conclusion that addresses the original claim with wording that can be understood by those without the knowledge of statistical procedures. What does that mean? You want to be able to explain it to your friends, okay, and not your fellow statisticians. You want to be able to say something to them where like, hey, this is what this means. So here, our XSort method of gender selection. There was not sufficient evidence to support the claim that the XSort method is effective, increasing the probability that a baby girl will be born. Now, coming up with these conclusions is a little bit tricky. So you can use this flow chart on your exam, and I would suggest that you print this out and actually have it on hand. You can use this to help you formulate the conclusion. Here, our claim was that it was strictly greater than. So does our claim contain the condition of equality? Remember that claim was that it was strictly greater than, right? So no, it does not contain the condition of equality. Great. Did we reject the null? No, we failed to reject the null. So there's not sufficient sample evidence to support the claim. Now remember, our claim is that this XSort method actually works. We can't support that. Even though 58% is better than 50%, and that supports what we're actually trying to say, it's not good enough. In other words, it's that 58 out of 100 girls could have happened by chance. That goes back to our rare event rule of inferential statistics. If that could have happened by chance, then we have to make our assumption that what originally happened was incorrect. But it was close, right? Remember, it was 0.0548, and we were looking for a threshold of 0.05. Usually what happens when you report your results in a professional manner, you only report your p-value, and then the reader makes conclusions based on that. All right, so let's finish this up. We never actually conclude that a hypothesis test is a statement of reject the null or fail to reject the null. You got to put it in layman's terms, be able to explain it to your friends. We want to make sure the conclusion uses simple non-technical wording that addresses that original claim. Now, talked about this earlier, but some texts use accept the null. We're not proving the null. Fail to reject says that we're more correctly that the available evidence is not strong enough to warrant rejection of the null. We're not hitting a specific target here. We're creating a range of values that we're going to say, yes, in this case here, we're going to reject the null or we're going to fail to reject the null. And that is a range of values. Key concept here. We have a complete procedure for testing a hypothesis made about a population proportion. And this section uses components introduced in the previous section for the p-value method. We're not using the traditional method, and we're not using the confidence interval method. There's a lot going on here, and I don't expect you to, having watched this video, understand everything that you need to about hypothesis testing. What I do expect, however, is that you're going to watch the next videos that I have for you and look at the examples and go through them. And by going through the examples, they'll step you through those processes on how to do a successful hypothesis test. Thanks.